Okay, welcome back. I wanted to remind, you should have gotten a couple of emails from me today. First of all, what's happening on November 5th? Well, I was going to say Guy Fawkes' Day, but that's just me. That's a real holiday in England. But yes, you're right. We'll celebrate it by having a midterm. And that'll be in class, closed notes, closed book, no calculator, derivation type questions, and short answer type questions for the, based on the material. And I think, what did I say based on the material through? The 22nd. That's 2 weeks before the exam. Okay? That's why I did. That's why I picked that date. It was 2 weeks before the exam. We'll freeze it. The other thing I sent you out was an announcement that I posted the computer project. And let me remind you that at the end of the semester, on the last day of class, we're going to have another test, and the test will be on the homework problems. And so I'll just be really clear. We're going to have 3 problems on that test. It's worth 30 points. 2 of the problems are going to be homework problems, and one of them is going to be a problem that's based on that computer project. Okay? And so if you do the computer project, I promise you the question will be very simple. Okay? I gave you a bunch of questions to do, and so it'll be a fairly simple, just sort of a check that you did the work on that. And then similarly for the homework. Kind of boring, I know, but that's just the way we're going to do it this year. And then there'll be a final exam, and the final exam will be cumulative, and it'll be much the same as the midterm. Okay. All right. Any questions about that? Any complaints about that?
Will we be able to keep our midterms? Is that
Sure.
something we can study off of?
Sure. Well, you'll give them to me.
Okay.
I'll grade them, and I'll give them back to you. And then you can, I would recommend you laminate it, and treasure it. 20 years from now, I expect you to be, enjoying the warped questions that your professor came up with over a midterm on Guy Fawkes' Day in 2014. How many of you have heard of Guy Fawkes' Day? There you go. What's Guy Fawkes' Day? What?
Lethal Vendetta.
Lethal Vendetta. Yes, it was, actually.
Oh, definition.
Oh, okay. Thanks. It was a plot to overthrow the government, the Houses of Parliament. There was they mined a tunnel underneath it and packed it with dynamite, and it was found. So now every November 5th they build a big bonfire, and they put a dummy Guy Fawkes on there. They burn him, and then they set off lots of fireworks and stuff. It's kind of like our 4th of July, but a little more anemic. So, okay. Anyway, a little bit of trivia just to warm up the crowd tonight. We are taking plane waves, and we are tossing them against the wall. And what we're doing is we're really doing a certain type of superposition. So do you remember I build the plane wave as a Fourier component, and since everything was linear time invariant, what that meant is I can, once I have a certain type of solutions, I can build up any type of solution I want based on the circumstance. And I showed you how things could get kind of weird in polarization, because you're not only adding up terms, you're adding up terms in vectors and in phase. So strange things can happen. Okay. These superposition problems come about from the fact that I've got a wave going in one direction, and when I hit a surface, there's going to be at least some of it that bounces back off, and I'm going to have a superposition of a forward-going wave and a backward-going wave. It's a good thing we solved the wave equation with that plus or minus kz in the exponent, right? Because now we have both of those solutions. The other thing that's kind of interesting about these these reflection problems is that we get to use our boundary conditions. And so it reminds us a little bit about what would happen on a surface with charges and fields and so on and so forth. Okay. So last time we did a perfect conductor. I waved my hands a little bit about and sort of gave you a small correction factor if it was not a perfect conductor but just a very good conductor. One of the interesting things there was that the beam actually, the plane wave actually penetrated a little bit into the metal. And that's of course what you would want to, that's what would explain things like damage. If you shone too much field onto a metal surface and it started to melt, then that's an example of that. And I've done that with lasers, and I've gotten paid to do that with lasers, which is even more weird than you can think. But anyway, so that was a perfect conductor. And now what we're going to do is we're going to shift gears and we're going to look at a perfect dielectric. Okay? And so same kind of picture. I have to make sure am I in focus? Pretty not too bad. The blurriness is from my handwriting, it's not from the camera. So, material 1, material 2. Sigma 1 equals 0 and sigma 2 equals 0. So there's absolutely no loss whatsoever. I reminded you, I'll just use that for a second to remind you that in my book, sigma can be two things. Right? For a metal, sigma is a loss due to the conductivity of the metal. That current is actually flowing in that. But in general, more generally, sigma is my go-to for loss. So if I had an imperfect dielectric, I could still characterize that by a loss without substantial current flow. Okay? So two different interpretations of what that one constant might do. One, a very literal interpretation of the conductivity of a metal, and the second, not as popular, but certainly reasonable from a mathematical perspective of a loss term, due to dirt and smudges and ink and stuff like that that might go on in there. But in this case, we're going to have the perfect one, so it's going to be lossless. The other two coefficients to describe it is a mu1 and a mu2, and it's not that common to come across a dielectric that has magnetic properties. I mean, you have to work pretty hard for that, to kind of happen. But it does. It does. There are magneto-optics, and absolutely that can happen. But for most of the problems that we consider, this is a block of glass, and mu is going to be mu naught. So. Where things get interesting, though, are the epsilons. And the epsilons, of course, can change. And that's probably how we're defining. That is, in fact, how we're defining the step function to go from an epsilon 1 up to an epsilon 2. Okay. So we know that we know that just to do a review, we know that the impedance of this material. What is impedance? How do I calculate that? Square root of mu over epsilon, L over C, the square root of mu over epsilon. That gives me the impedance. How much for free space? And for anything else, it's going to be higher or lower? Lower, because the epsilon's in the denominator. And then and so we have an impedance mismatch between these two. So I'll have one type of capacitive loading here and another type of capacitive loading here. And then the other thing to note is that what's the speed of propagation of the wave in terms of mu and epsilon? 1 over the square root of mu epsilon will give you the speed of propagation. And so we see that the speed of propagation will be different in this material and this material. Okay? And so if we go from a lower to a higher material, it's in the denominator, and so a higher epsilon will give me a lower velocity in here. Okay, so those are the mismatches that this wave will see. And I'll start the whole problem by picking up my plane wave and tossing it against it, and so I'll have an E incident and an H incident. Okay. This is my z-axis, and that'll be z equals 0. And I know that I'm going to have this mismatch, and I've kind of seen this, we've seen this enough in the real world around us. We can look through a pane of glass, for example. So we know that there's going to be some transmitted wave going through there. I can shine a laser beam or a flashlight through a window, right? And then also you've seen this as well. If you go up to a window and look at it and focus on the surface of it, you'll see a faint reflection of yourself. And so we also know from experience, if we couldn't guess from the situation of the problem, that there'll be a reflected wave and a reflected electric field and a reflected magnetic field coming right back at us. Okay? And as we'll see in a little bit, normal incidence really is such a very perfect case of symmetry. Any little breaking of that by a millisradian and all bets are more or less off, certainly as you get further back. But so it is really a very symmetric, overly symmetric situation to think in terms of perfectly normal incidence on either what we did last time, a perfect conductor, or tonight, a dielectric. So I just want to make sure you know what a fake setup this is, right? It's you have to work very hard to align your mirror or your flat surface. How many people have like a satellite dish to see TV with? No, nobody? Nobody has direct TV has anyone ever installed one of those? Oh, you should try one weekend. It's a lot of fun to be perched on a roof about to fall over and trying to aim this thing at a satellite. It's both, it's not fun, but it teaches you a lot about these kinds of alignment issues. All right, so the propagation constant, or I guess we've been calling it the dispersion relationship, right? The dispersion relationship, that little e to the k business, that's going to equal the frequency times the square root of mu epsilon in general, right? And so we always look at frequency being given. Frequency is given, and then what adjusts is the k. And so what adjusts is this is 2 pi over lambda. So what adjusts is the wavelength in the material. Right? So the wavelength will shift, and that makes sense. That's all related back to the speed of propagation of these fronts. If the speed gets slower in water or glass, then the distance between a phase front, the peak of the phase fronts, is going to compress. It's going to get shorter. Okay, so it's a kind of common sense, but worth thinking about a little bit. And so those are the equations for the dispersion relationships in 1 and in 2. And you'll notice that k and the e to the kz term will change across that boundary. And that's something that we'll have to think about. Okay? And then I'll also write down our etas. So we can see explicitly the change in the speed, change in the wavelength, change in the impedance across the boundary. Okay? All right. So now in material 1, for z less than 0, my total field will be an incident field and a wave that's moving towards the surface. That's what the minus sign means. I have a positive z going in this direction. And then plus a reflected wave and I'll pick the x-axis, the x as the polarization of the field, the direction the electric field is pointing. And then this is in material 1. H1 of z will equal minus the curl of E over I omega mu. That comes directly from, this comes directly from the time derivative, Fourier transforming the time derivative, or substituting in e to the I omega t. Same thing, 6 one, f dozen the other. And then the mu comes about from the b to the h conversion. And so this is going to equal 1 over eta 1 when things kind of get cleaned out. And if you look back over your notes from last time, you'll see that this is perfectly consistent with what we had for case number 1. There's nothing new here. This is just a little bit of a review. And all I'm doing is just kind of saying, hey, I've got an EI and I've got an ER. Notice that I'm not even suggesting that I know the relative values yet of ER and EI. Okay? Although if I find it out here, I also know it from there. Oh, I guess I don't want to bore you, but I do want to remind you that, this works out nice units-wise. Volts per meter, H is in amps per meter, and going from a volts to an amps means that I divide by an impedance, by ohms. Right? So that's kind of physical and nice. Or maybe it's, yeah. Now, in material 2, where z greater than 0. And please notice what I'm doing, which is I'm letting this material go to infinity. So there's not a lot of real-life applications where this is going to hold. I suppose if I stood over an ocean and I shone my flashlight into it, that would be that would be one thing. But even that would be very lossy, and I wouldn't have this. Okay. So there's not a lot of applications of this. Maybe a 9 megameter fiber optic cable. That's pretty deep. 9,000 kilometers across the Pacific. So, and just so you know, if I end this, then I'll have the same kind of impedance mismatch. And I'll have reflections here as well as back here. And that can get to be sticky. And I'm going to give you I'm going to punt on that for at least a month. Okay? Because I have a very different way of analyzing that problem. Okay? All right. So in material 2, the electric field is some amount of the field that's transmitted and if it's a simple enough material and we are really perfectly at angle of incidence, then there's no reason to expect the electric field to change its orientation across the boundary. Okay. So there's all the fields that we need to know, and it looks like if I guess I could say that I could reference everything in terms of an E incident. How many volts per meter am I picking up and throwing at the wall? So what I really need to know is I need to know the relative amount of ER to EI, and then the relative amount of ET to EI. That's what I need to do. Oh, notice one other thing about this. There's this little thing here. The K1s and the K2s. So again, my dispersion relationship changes. And so my propagation constant, or my degree of freedom, my K, changes. And then notice that the conversion from E to H, there's an eta in there, but in material 1 it's eta 1, and in material 2 it's eta 2. Okay? So the subscripts, pay attention to the subscripts. There's two places that it changes, in the K and also in the impedance, eta. Okay? And so that's going to have ramifications on our solution. Now, boundary conditions. Across the boundary, the electric field has to be conserved. That's what we found last time. It's a tangential component of the electric field, conserved across the boundary. And if I evaluate z equals 0, this guy is 1, and this guy is 1, and z is 0 here, this guy is 1. So I have E incidence plus E reflected must equal E transmitted. And if I divide through, then I'll call that equation 1. I'll call that equation A. Okay. So 1 plus ER over EI is equal to E transmitted over E incident. Kind of a trivial expression, but one that we can do a lot with. For H, we know that we see that the normal component of the H field, the difference between them may be due to a current. Okay. But in this problem, sigma 2 is equal to 0, and sigma 1 is equal to 0, so there's no conductivity to allow a current to flow. So for that reason, this is going to equal 0 for our sigma equal to 0. And think about the fun we're going to have if we relax that. So this is kind of interesting. H1 at z equals 0 is equal to H2 at z equals 0. That's markedly different from what we had before. Okay. So 1 over eta 1 times E incident minus E reflected. I'm looking at this equation now, and this equation now, for the H's. Sorry. And this can be rearranged here. So to do that, I'm multiplying first through by eta 1. So I collect all the etas on one side. And then I divide through by EI. So I have everything's nice and dimensionless. So A and B, without much work, gives me two equations and two unknowns. Right? So what I'll do is I'll say rho will be the reflected wave over the incident wave, these two terms. And tau will be these two terms, the transmitted wave over the incident wave. So these are the field reflection, transmission coefficients. There's my reflection, there's my transmission. Some books like to use R and T. Some books like to use gamma. Thank you. But I'll use rho and tau. Occasionally I'll use little r and little t. I really resist the urge to use a capital letter. Because this is field. It's in volts per meter. And if I want to look at the Poynting vector, watts, then that's a different ballgame. Okay? And we're going to explore that today. So A and B become nice, simple-looking creatures. I mean, so cute and nice. You wouldn't expect them to give you any kind of trouble, but there's interesting stuff there. If I add the two together, I'll eliminate the rho for a little bit. And then I can solve for tau in terms of just the material constants. Right? Solve for tau just in terms of these impedances. Okay, so that's the amount of field transmission that goes across the boundary. And if I take this and I sub into A, I want to solve, now what I have is expression for rho in terms only of the material properties, the impedance there. And so what I'll do is I'll solve for rho. So I'll subtract 1 from both sides, and I'll write 1 as a common denominator. And if I clean up the numerator here, I get an expression that looks like that. So now I know how to calculate. Now I know how to find my rho and my tau, which is my ratios of E1 and E2, of EI over ER and E transmitted over EI. So in material 1, I have that, and this I introduce a little factor of rho. Not all my field comes back at me. There's a degradation, depending on how much difference there is between eta 2 and eta 1. Okay. And then I can explicitly write what my E2 is. So my Poynting vector in material 1 and I'll look for the time averaged, so I'll take the complex conjugate of the second run. E1 is in the x direction, H1 is in the y. Crossed it over, it's going to get in the z direction. Here are two terms that are that can come together. This will be 2i rho times the sine of twice k1z. But for the time average part, I'm looking at just at the real part of this, so that guy goes away. And so there's my answer. V squared over r times 1 minus rho squared. That's my total Poynting vector. Now, if I'm just interested in the incident power, then I just repeat the process with a simpler electric field and magnetic field. These guys cancel out. And if I do the reflected wave, I get that, skipped a step, really just like this. The minus sign comes from a minus a x crossed with a y. And that's nice because the direct minus sign will tell me the direction of the power flow. Incident, positive, reflected, negative. So for once that's not a mistake. I want to celebrate that. And if I look at SR over S incident, the time averaged, you'll see that I'm in the same material. This factor of 2 cancels, and this is just the same thing as rho squared. And this we might give a capital letter to, and this is the power reflection coefficient. Okay? And I'll flip back so you can write this. You see this rho squared here? That's my power reflection coefficient in the overall Poynting vector, time average Poynting vector in material 1. Okay? Now this is all for immaterial 1, for z less than 0. So in material 2, the time average Poynting vector This positive sign is because of this complex conjugate here that's required for the time averaging. And this simplifies to 1/2 EI squared tau squared over an eta 2. Now I have a SI term here, and this is EI squared over twice eta 1. The eta 1 came from the magnetic field in material 1, And I have an eta 2, which came from the magnetic field of material 2 for my time averaged Poynting vector S2. So if I want to look at S2 time averaged over S1 time averaged, this is the amount of power that's transmitted into the material. So SI is EI squared over twice eta 1. So I'm flipping that around. And so this is my power transmission coefficient. And it's important to notice that it's not just tau squared. It's tau squared multiplied by the ratio of the impedances. Okay? So it's easy to forget that. But it's important for power conservation the incident power should equal whatever power is reflected plus whatever power goes into material 2 or is transmitted. If I divide through, I get the ratios of the power coefficients, power reflection coefficients, power transmission coefficients. So this is equal to rho squared plus tau squared eta 1 over eta 2 equal to 1. And I think we said that eta 2 minus eta 1 over eta 2 plus eta 1 was the reflection coefficient. Field reflection coefficient, so square that, gives me that. And this will equal 1. Okay? To show that, and I'll let you do this at home, to show that you want to put everything on top of a common denominator. So you're going to have an eta 2 over an eta 2 here, and then you'll have an eta 2 over an eta 2 here. So multiply through by, put that over a common denominator. Then you're going to have an eta 2 squared minus an eta 1 squared. Eta 2 squared minus a 2, eta 1, eta 2, minus an eta 1 squared. And then you'll add to that a twice eta 1, eta 2 squared, eta 1. And you'll see that that cross term will flip sign. Pull out an eta 2, that cross term will flip sign. And then you'll have eta 2 squared plus 2 eta 1 eta 2 plus eta 1 squared, which will turn into an eta 2 plus eta 1 squared, and that's equal to 1. Okay? So, looks a little funny, but it does, in fact, conserve power. So that ratio of the eta 1, eta 2 is critical to conserving power. And it comes about really naturally from the math. Now, if I have a lossy situation here, if I'm doing this in terms of lossy materials, then everything stays pretty much the same, except my epsilons. I can put my loss in terms of an epsilon, a complex epsilon, or more readily, a complex impedance. So in addition to having an L over C, I'll also have an R in there. And so my eta will be complex. So just turn your eta into a complex number, and that will give you the degree of freedom that you need to calculate all the properties, the reflection coefficients and transmission coefficients. Now, it's usually the case that an electric field is an electric field is an electric field. So whether you're at 60 hertz, whether you're at 60 megahertz, or whether you're at 60 terahertz, you're going to have about the same propagation. But in practice, you have different tools. And principally because the wavelength changes, certain things are easier done in the gigahertz range one way and a different way when you're in the optical range, 200, 300 terahertz. The wavelength gets so small that you can't really discern very easily the wavelength of an optical signal. And if that's the case, then these reflection values, in particular the power reflection values and the power transmission values, are what you measure. I mean, in the early day with high-powered lasers, there was a unit of measure called a Gillette. And Gillette made razor blades, and the number of Gillettes of your laser beam was the number of razor blades that it would burn through. Okay? Uncalibrated, but it was repeatable. Okay? So you can make measurements easily. You know, if you don't know the wavelength, you can make measurements pretty easily with R, trace it down to the rho and the tau, and then you get all your material components. You know what your fields are doing from power on down. Okay? But if you're at a gigahertz, you're working with a foot, standing wave of 6 inches, you can build a probe of a millimeter, and you get a pretty good profile of your standing waves, which will emerge with the reflected superposition, with the superposition of the incident wave with the reflected wave. So what was usually measured in the low frequency range, like gigahertz range or hundreds of megahertz range, was the standing wave ratio. And this is equal to the maximum value of the electric field divided by the minimum value. And notice that since H is equal to E over eta, and you're in the same material, it's the same for the ratio of the magnetic fields. Now, if you go back to our expression for the electric field, the maximum that's going to happen is when these guys are in phase. And so I'll find some Z where EI and ER add together. And then I'll find, to get the minimum, I'll find some place where this is out of phase of that. So EI will minus ER will be the minimum. Okay, since I'm only dealing about the absolute value, and since I'm doing this experimentally with a probe, I'll find the max and I'll find the min and just fit that to that. So this will equal the absolute value of the incident wave plus the reflected wave, and then where they cancel, where it tries to cancel, like that. And if I divide by EI, and I should be a little careful about the absolute values. So the standing wave ratio can be written in terms of rho. And I can go back the other way too. And write the rho in terms of the standing wave ratios. So, depending on what wavelengths you're working at or what frequencies you're working at, you may find it easier to measure one and calculate the other, or measure the other and calculate the one. Notice this minus sign in the denominator. If I have a perfect reflector, I'll have an infinite standing wave ratio because I will have an absolute null, an absolute zero at the minimum. And that's what we found, that's what we saw last time. And if I have no interface, I'll get no reflection and be 1 for no interface. Okay? So those are the two limits of that. All right. Let's break symmetry now. We'll do a perfect conductor, and we'll do a non-zero angle of incidence. So, there's my conductor. This is normal to the conductor. And I'll have a wave coming in here. And I'll characterize this wave. Well, I'll have a wave coming in here, and I'll have a wave reflecting back over here. And I'll have an angle of incidence, and I'll have an angle of reflection. Now, the this can be looked at as a collision of a plane wave with a perfect conductor. And two things have to be conserved with this collision. So, conservation of energy, and that will imply that the incident frequency must equal the incident reflection. Okay? And I'll dip into quantum mechanics just a little bit. If I multiply both sides of that by h bar, Planck's constant over 2 pi, I get the energy of a photon here and the energy of a photon here, and the energy should be conserved, which means that there should be no change in frequency upon that reflection, if indeed I have conservation of energy. Okay? Well, the other thing that needs to be conserved in this collision is momentum. And momentum is that the K incident must equal the K reflected. If I multiply these by h bar, then I'll have the momentum of the incident wave and the momentum on the reflected wave. Okay, look at the units if you want to do that. Joule seconds times divided by meters squared. I'm sorry, divided by meters will give me units of momentum. And this means that theta incident will equal theta reflection. Okay? You can solve this, you can derive this in a variety of ways. A least time integral, for example, or this conservation of momentum, for example. But it comes out to something that we kind of know, and something that you might learn from a squash court or a pool table or a basketball court. If you bounce pass a ball to your teammate, the angle of incidence will equal the angle of reflection. Or if you're bouncing a ball off the rail of a billiards table and you don't have any spin on it, the angle of incidence will equal the angle of reflection. Okay. But there's one other thing about this momentum case. And it's kind of looking at us in this picture. The direction that this guy is going is different from the direction that this guy is going. So before, I had one direction of propagation. In all my normal incidence problems, I had a k times a z. And I haven't even written down my x, y, and z here. But if I pick this guy to be z, I sure as heck cannot pick this guy to be z. So what that means is that the k must be a vector. And that's consistent with the interpretation of momentum. Momentum is a vector quantity. It's m times the velocity. Velocity is a vector. So k will go to a vector. Kz will be an x component of k times x, plus a y component of k times y, plus a z component of k times z. And that can equal the dot product between k dotted with a vector r. So the incident wave and the reflected wave we'll now have these dot products in there. So that's a huge leap. That's a huge leap, and it's just demanded by the fact of our geometry here. All of a sudden, that nice little dispersion relationship that we had is now looking like a vector to us. But it's actually quite convenient, because now we can track the location, the direction of the beam is going through K. So that's kind of a, if we allow ourselves to take this leap and recognize KZ as just one term of a dot product, and there are two other terms of the dot product, well then we're pretty much okay. Well, let me pick an axis here, and coming out of the board, X will come out of the paper like that. So X is sitting up like this, Y here, and then Z is the normal of the geometry. And I'll have a K vector on the input, and I'll have a K vector on the output there. And I know that this theta is equal to this theta. So I'll decompose this K into two components to line up with my coordinate system. Okay? Actually, hold on one second. Let me redraw this. So I think it's got to be bigger. That's theta, and that's theta. And then I've got a K going here, and I've got a K going here. Okay? So I'm going to decompose this K into the two components that fit with my coordinate system. K is in the XZ plane, or the YZ plane. So I'm going to have a K that's moving this direction, that's the blue one, and a K that bounces off of the surface, and that's the red one. And if this is theta here, then this is theta here, opposite interior angles. And this K sub y is equal to K sine theta. And this K sub y here is equal to K sine theta. This K sub z, and notice that it points in the minus z direction, is equal to minus K cosine of theta. And this positive K sub z is equal to positive K cosine of theta. Okay? So that's what my momentum vector is doing. Okay. Now, I have to, this breaking of symmetry here is small, but it has a really significant impact on the fields. Okay? So, I'm going to call this case 3A, and I'm going to pick an electric field. So I'm going to pick this E field to be the perpendicular to the direction of propagation. So I'm going to orient it into the x direction here on the input. Okay? So that's EI. Now with the decomposition, that incident electric field has a value and a propagation term that looks like that. Now let me just back up for just a second here. If my electric field is pointing here, and if it's coming in at an angle of theta with respect to the normal, then what's my H doing? My H has to be perpendicular, E cross H, to the direction of propagation. The wave coming in here doesn't even know the metal surface is going to hit the metal surface, so nothing weird about that. So E crossed with H puts H sitting out in this direction here. Now you see why I had to specify a direction of the electric field relative to the direction of propagation. This is a funny business, but it looks like H, just because of the metal surface is there, and because of the geometry, H is, it's also perpendicular to the direction of propagation, but not necessarily to the plane of propagation. So this E here, transverse to there, it's called this is called the TE case, transverse electric case. And you see that even though H is perpendicular to the direction of propagation, it's not perpendicular to the surface. Okay? So H is going to have a component in the z direction and a component in the y direction. Right? So in this particular instance, I'll have an EX, what did I say, an H sub z, and an H sub y. So z and y are perpendicular to H. I'm sorry, z and y are perpendicular to x, so H is perpendicular to E, or at least it can be, and it is. Okay? So in this particular example, I have a definite EX, and I've got two of my components of my H field. Okay? Remember that accounting. Remember that accounting. Okay? That way? So, in general, I've broken symmetry now. So everything's on the table. In general, I'm going to have an X field, an X electric field, a Y electric field, and a Z electric field. And I'm going to, and correspondingly, even though this is going to be perpendicular, I'm going to have an X H field, a Y H field, and a Z H field. So it looks like in this case A, I'm accounting for half of my total problem. I still have an H sub X to worry about. Oh, and I also have an E sub Z and E sub Y to worry about. Okay? If this is called the TE case, the other is going to be called the TM case, transverse magnetic. Okay? All right. In reflection, now the y sine theta doesn't care. That's just going to be right there. The flipping of the sign happens with the z direction, right? So the red component of K is moving in the minus z direction. However, the red component on reflection is moving in the positive z component. So I have that. Okay. So now, at the origin, y, z equal to 0, I'm going to have E reflected plus E incident equal to 0, or E reflected is equal to minus E incident. And so if I plug these guys, if I add these guys together, and I solve ER equal to minus EI, worry about this positive here and minus here, do a little bit of algebra, I get two pieces of the puzzle. I get a standing wave along the axis Z, like I had before. In fact, if cosine is equal to 0, normal incidence, that'll be 1, and I'll have exactly what I had before for my standing wave. And then I also have a component that's a traveling wave, and that goes in the y direction.